Okay, let us start this lecture. It is the last lecture in this semester. One thing is that next Tuesday, right? There will be the lecture as usual as before. Next week, the Tuesday lecture will be a revision. Okay, let us start for today. Okay, first of all, we recall what we have last week. What we have on this Tuesday. That a system can be described in state space. And then the in-out relationship depends on the function. So it is very important that for the transfer equation to exist requires this matrix to be invertible. So it is because the transfer function is the output divided by the input. So we have the output equals the GS and then US. Okay. If the GS does not exist, then YS cannot be controlled. So agree with this. We need a solution that exists. Otherwise, the output of the system cannot be controlled by any means. Okay, agree with this concept, right? We need a mathematical transfer function to exist. Okay, then we look at the control. Okay. Control design based on state space. So for example, so we use the water tank system again. So the water tank, the area A1, A2, and then the height of the water level H1, H2, and then we have a Q, the inlet, and then we have the resistance between the tanks, and then a resistance at the outlet. Okay. And then in the previous lecture, we know that we know that in state space, in the state space we have the x dot equals ax plus bu. And then we also let, okay, just a numerical example. If we have the a equals something easy, minus 1, 1, 1, minus 2, okay, something easy, and then b equals 1 and then 0. And then the output, y equals cx. Then with c equals 1, 0 for tang 1, and then c equals 0, 1 for tang 2. So we start from here, right, and then to try to work out the design of the system such that it meets the requirement. So in previous studies, we always look at the system like this. And then this y, and then the reference, and then the feedback. The important thing to note is that this is the output. So this system, we call this, more precisely, it is output feedback control. Okay, now in state space, we have the system it gives us the x and band, and then we construct the feedback. Now we call this simply the k, and then the reference. In particular, we call this the state, okay, where the output is over here. Then we call this the state feedback. Okay, it is different from the in the previous lectures that we in the previous lecture, we always consider using the output as the feedback. Right. Now in the state space design, okay, we have the state going through a feedback, and this is the simplest form. Okay, it is simple, just gain factor. Right. And then we also consider something simple, right? We let R equals 0. So what is meant by putting R equals 0? Is that, for example, a set point at some reference so R equals 0 is just a shift of for example, R equals 10, right? We just shift alternate by 10 units. Later on, we will look at if R is not 0, right? So we start from the simple case. First of all, the feedback is just a gain factor. And then the second simplification is that the reference is 0. Okay? So now what we have is that the control to the system, the controls to the system. Now U equals minus Kx, and that depends on the state. Then dx dot equals ax plus b minus kx. Okay, because the control U equals minus kx, so it becomes ax minus bk of x equals a minus bk of x. Then we define another system. Yeah. U equals k. This is the feedback we use the This is feedback we use the minus. So U equals k times x and then minus. So this is as if having a new system. A new system, we call it the AF, the feedback system. By using the feedback from the states K, we construct as if it is a new system defined by the matrix AF. Okay, so far, agree with this? We create a kind of new system using the scaled feedback from the states. Then we ask the question, right? What would be the response of the new system? The new and so we always know that, or from recalling, right? The response depends on characteristic equation. Now the characteristic equation is the determinant of Si minus A feedback. Okay, this is the feedback system. Okay, agree with it. The system response depends on the characteristic equation, and the characteristic equation is the determinant, right, of this matrix containing the feedback system. Okay, for the example, for the example, so we have two states of water levels. Okay, we have two water levels in two tanks. Therefore, the gain of the feedback K should contain two elements, K1 and K2. And this matches the number of states. Okay. So it is important to note that. Now, the gain factor K contains two elements. Okay, it is also in contrary to the output feedback case. And then also note that the feedback, okay, is A minus B K, the original system, and then we subtract the B and K. Okay, then the Si minus A equals, so this is Si, and then minus AF. And then the AF is the A matrix. In our example, it is this one, minus the B matrix, and then K1, K2. Okay, then we work it out carefully. Then we have S plus K1 plus 1, and then minus 1, K2 minus 1, and then S plus 2. Now it is important to note that this multiplication becomes K1, K2, and then 0, 0. Okay, is the a column vector multiplied with a row vector, and then we have a square matrix. And the determinant is determinant of Si minus A of feedback. So it is S plus K1 plus 1, and then S plus 2, and then minus 1 times K2 minus 1. So it is equal to the S squared plus S3 plus K1 plus 2 K1 plus K2 plus 1. So if we work out the calculation here, find out that the determinant equals this. So what we can see here is something very important, right? K1, K2 are design factor, are design parameters. And then we also look that K1, K2 affects the system response. Because the determinant or something, it is our characteristic equation. And then of course the characteristic equation determines the system response. Then what we can do is we can specify our response. Then find out K1, K2. So how we specify the response, for example, okay, we let pulse at -1, -3. So we have negative pulse, and then it must be a stable system. Okay, and then where to put the 1 and 3 is also a design decision. So with regard to the system specification, so what we can specify, the steady state error, the overshoot, the rise time, or the settling time, etc., etc. And then we generally we know that in the J omega in the S plane. Okay, so here this a pole, a pair of pole, we have the oscillations. So somewhere here it is a slow response. Somewhere here it is faster response. And then if we specify our damping and then the natural frequency, so that is our theta and omega n, right? The characteristic equation becomes and then we can factorize S plus A and then S plus B. Okay. Then place pose at minus A and then minus B. Okay, agree with that? Right. The location of the pole determines the system response. Right. And in addition to find out the system response from a given system, we can specify the response and then we find out the gain factor. Okay, this is the key concept in the design of in the state space design of control systems. Okay, and then for this example, we let pose at -1 and then -3. Then the characteristic equation is S plus 1 and then S plus 3 equals S squared plus 4S plus 3. Okay, and then we compare to characteristic equation of feedback system. Which is square plus then it is quite, and then it is straightforward, and then we match terms. And then matching the terms. Matching terms, we have 4 equals 3 plus K1. Then we have K1 equals 1. And then also for the second part, we have 3 equals 2K1 plus K2 plus 1. And then we find out that K1 is equal to 1. Then we have a 2 plus K2 plus 1. And then it gives us K2 equals 0. Then we have K equals K1, K2. So it is 1 and 0. Then the system, then the feedback system will respond as if the poles at -1 and then -3. Okay. So far, any question on the state space design up to this point? Okay, then we consider another case. Another case. So we let the we specify a pose at -2 and -3. Then what do we expect from the response of the system? What happens then? Okay. Then we repeat the design process again, right? Then the determinant of the Si minus AF should be, right, required to be S plus 2 and then S plus 3. And then as before, and then we match terms. Match terms. So this time we have 5 equals 3 plus K1. So K1 equals 2. And then we also have 6 equals 2 K1 plus K2 plus 1. So it is 4 plus K2 plus 1. And then we have K2 equals 1. Then K equals 2, 1. So how it compares to the previous case? We know that because 2, this is further to left of S-plane, and then it should faster. So agree? We put the pole further to the left, while the other pole remains the same. That is to say we want a faster response. If we want a faster response, we have the gain factor resulted in 2 and 1. So what happens now is that we recall that U equals minus K of X. Okay. So when state is limit in some range, the minimum between minimum and maximum. Then we see that, okay, U for k equals to 1 is larger than U for k equals 1, 0. So what we can say is that a faster response is a pole further to left, the left S-plane requires higher control energy. So the faster and the higher. Okay. So, okay, the response and then the energy. So need to be a trade-off, or okay, agree with this. We want a faster response. Oh, right, but this faster response is not free, right? We need to apply a higher energy into the system so that it can respond faster. Okay, any question on this? Agree with this? Okay, then we look at an alternative design procedure, or it is a simpler procedure. So it is based on the Ackermann's formula. So it especially requires, given a system matrix, the A must be in some particular form. And then the B matrix must be in this form. Okay. So it is required in this form to apply the formula. So it is very important to have this form or this condition satisfied. Then what we can have in this form is A minus BK. So it is 0, 1 minus A0 minus A1 minus BK is 0, 0, K1, K2. Okay, so it is then 0, 1. and then also this is the feedback system, and then the SI minus feedback. So if here's minus so this equals so we arrive at this form. And then the determinant is of SI minus AF. Determinant is so it is minus 1. This plus A0 plus K1. So if the if the specified characteristic equation is if it is then we can match terms. So the alpha 1 equals so this one equals S squared plus S. So alpha 1 is A1 plus K2, so K2 is simply alpha 1 minus A1, and then alpha 0 is so K1 equals so what we see here that the calculation is simple. But must be in the so-called controllable form. For this particular name, then we have the 0 minus A0 minus A1. We must have this form, and then B equals okay. So far, any question up to this stage? Is that okay? Yeah. No. It is another case. If we can put the original into this form. Oh, sorry. Okay. So if can put A in this form, it is very important to have another form. For this formula to apply, we must require the system matrix represented in this form. If we have originally that form, we can do a transformation from one form to another form. For example, we see that in the block diagram how we derive the matrix equation, right? We saw 3 cases of possibilities to represent the same system. Remember last week? Yeah. So the important thing is that if we want to apply this formula, okay, this formula is simple in calculation, but we need this kind of matrix because of the so many zeros that add 0 and 1 so that we can do the simplification.
Yeah, but let's say you're given a matrix with all 4 indices filled.
Yeah, in that we will let me see. It is in one of the somewhere in the problem is that we do not have time to cover that. It is so in one of the lecture handout, we have the this one state space and transfer function. In this lecture handout, we have the similarity transform method, right? That can put the matrix from one form to another form. Okay. Now, if it is not given in this form, you can transfer to this form. And then you can apply the Ackermann's formula because it is easy to calculate. Okay, another method. Okay, yet another alternative method. So it's given that K equals this form. And then where the term alpha, it is also a matrix, A squared plus alpha 1, A plus alpha 0, I. So here, the A is raised to the power of 2, right? So this is just for second order system. So if we have a higher order, and then this A will be raised to a higher order. Now, for this method, we do not need to transform, right? Now we just calculate the straightforward dB and then AB. So here it is no need to transform. So the B and AB equals 1, 0, and then A is minus 1, 1, 1 minus 2. This one, so this 1 and minus 1, 0, 1. So in the inverse of this matrix, so if we work it out carefully, so it becomes this one. Okay. So this using minor cofactor, and then adjoint. Then we can calculate the inverse. So again, if we require the poles at minus 1 and minus 3, the same case as before, okay, then characteristic equation is it also as before? Then we set this equation. And then we compare terms. Compare terms, we have alpha 1 equals 4 and alpha 0 equals 3. And then we have the alpha matrix equals A squared plus alpha A plus alpha 0 I equals A squared plus 4A plus 3I. Now we have the A squared equals, using the same numerical example, multiply by itself. So the result is this one. And we also have the alpha matrix equals 2 minus 3 minus 3, 5, 4. And then that is the A matrix. And then the 3 times the unity matrix. So it turns out to be this. Okay, so far. Then we put it back to the equation. for the game factor. And then the factor k is 0, 1, and then b, ab inverted, and then alpha. So it is 0, 1. And then the inverted matrix is this one. And then the alpha matrix is so calculate carefully. Then we have 1, 0. Okay. Then we have k1 equals 1 and then k2 equals 0 as before. Very important to note that this one. Okay, the 0 and 1 are just numerical examples. So it is not always 1 and 0. So for the control u minus kx to exist, needs k to be found. That is this inverse can be found. So if the determinant BAB is not 0, then K can be found. So we define B and then AB, the controllability matrix. Okay. Oh, sorry. Now, because the importance of this matrix, okay, we just define a terminology to describe it. So how important is the controllability matrix? So we consider the water tank system again. And then we have the pipe resistance R1, R2, and then A1, H1, and then A2, H2, and then the input Q. We have found out the system matrix before, and we just recall it. The A equals A1 R1, and then 1 A2 R1. This. And then we also found out that the B matrix equals 1, 0. Then the controllability matrix becomes so it is a B of an A, B. Okay, from the system, if pipe are between a tanks is blocked, then we have R1 goes to infinity. Okay, the resistance is blocked for this pipe if it is blocked. Then we have the A matrix becomes R1 goes to infinity, right? Then we have the 0, 0, 0, and then some numerical value of A22. Okay, agree with this? Because the resistance is infinitive, we have three elements in the A matrix become 0. Okay. Then the controllability matrix B equals some 0. So if we B matrix is 1, 0. So this one is 0, 0, 0, 0, all 0. Okay. So it is this one. And then the determinant of this matrix equals 1 times 0 minus 0 times 0 equals 0. So B A can not be inverted. So gain K cannot be found. So system is not controllable. Is it okay? Agree with this concept? Oh, sorry. Okay, so far, any question up to this point? Is that okay? Okay, for the very last part, right? For the very last part, so we have the system. The state X and then Y, and then we have the feedback gain. So if the R is not 0, then we need to have the control part for the R. Okay, for non-zero input, so we have the control to the plant, the input to the plant, E equals, okay, we temporarily let R equals 1. Then the x dot equals ax plus b r minus kx. So it is ax minus b k of x plus b r. Then it equals so it is the feedback system plus b r. So it is treated as the input instead of the U. So what is KR? From x equals AF x plus B R, we find the transfer function. C is and then obtain the steady state error. Then we adjust K for minimum steady state error. Okay. Okay, I think we might have to stop here. Right. And then next Tuesday will be a revision.
In the exam, one method you can use, or I can use any method that you teach.
Depends on the question.
So you will specify the method that
Maybe. First of all, I cannot tell you what will happen, what will appear in the examination. And then what I can tell you is that if it appears, then you will be told to use what method or whatever. I couldn't tell exactly.
What would you expect us to do in the exam? Like we use a method of repetitive trial to extract the file. We have to share with other people what also. Yeah. For example, yeah, I mean, in the assignments, for example,
You just try to and then discuss
so just taking three examples is enough. Yeah. So, and for all the equations like if it's a log absolute value of a equation, so like we want to show the peak frequency and the boundary frequency, etc. So we have to share all the process of solving the complex. Just share the question. They need to share how we in detail solve how we solve the complex equations.
you have to show people what things you do not just give me the number.
Yeah. Or share the what equation we get and solution how we make possible solutions.
The game eventually just Can I get the microphone? Thank you.
Yes.
The last question one asks, for what velocity range would there be that the frequency is not attenuated by 10 dB? But if the peak frequency is never above 10,
No, attenuation is from the peak. You count 10 dB from the peak.
so the peak isn't above 10.
Huh?
The peak isn't above 10.
And then you count 10 dB below that.
So
If it is free, then 10 dB below that is -7, right? If it is whatever,
so you're saying
below that,
10 below the peak frequency.
attenuation. No.
So you want it to be as long as the velocity means that you do not exceed a frequency where the magnitude is 10 dB. I mean 10 dB below the peak frequency, in this case it means 3 dB. Right. Thank you.
Let's clarify something about the assignment. So,
Okay, simply tell me what is your question.
let's bring up this which is so this part, this part, reduce oscillation. So oscillation only occurs in the system if one of the, well, if any of the roots are complex, right?
You just put the S equals alpha plus j omega.
So then,
Then you can have different cases.
right, as in, but like, as in oscillate.
So simplest thing to do is from you have 1 term, 2 term, 3 terms, right? Just try to cancel all 1 terms.
Cancel one of the terms. And that's by changing the value of this one, right? H2. But I find that if I H2, because like it doesn't completely cancel from the delta. Like it actually, like, I don't know. But when I do
Your closed loops, your feedback is the G times H. So you can put anything on your H, so that you can cancel part of the G.
right. Then, like if you, but am I meant to like calculate the transfer function of like the whole closed loop as like a single block? Am I meant to like put them into one big block?
What's different? It's the same system.
Yeah, because if I put it into one big block, it doesn't cancel out. It like, so can I show you my work and see if I went well?
I'm not going to tell you it's enough.
Can I show you my work and see where I went wrong?
It can only, I can only tell you after I resolve it and I mark it. I'm not going to tell you right now.
But as in, so in terms of looking for oscillation,
No, you try to find out a complete transfer function. Do it.
yeah, I did. But like it doesn't.
Then you can see that you can see the effects of the H and the G,
Yeah,
how they relate to each
I
other.
have that. It's like, wait, I can show you. I have this, right?
Yeah.
But then
So,
if I,
so it is affected by H3.
yeah, so if I put H3 here,
Huh.
then it'll cancel out the like one of the terms in this fraction. But then once you like do that thing where you move all the,
It is the denominator that is the terms and equation that affects the system.
yeah. Oh, so it's not this whole denominator here, it's just the denominator itself.
No. The denominator of the transfer function, it is 1 plus H2 H3 together. That is the characteristic equation.
Yeah. But then when I put in H3 here,
So if you change H3, that changes the characteristic equation, isn't it?
it does, yeah. But it
So-
doesn't cancel out anyway.
What do you mean by not cancel?
It's like,
So you have G times H3D,
yeah. But then,
then.
but you have to like change, you have to change the top as well. You have to put G on
But
the top.
by that time you change H2.
Yeah, I have changed H2. Wait, can I show you the cookies just so it's not going to cancel, like I couldn't get it to get, can I show you real quick?
No, you. The concept is the numerator of the transfer function is different from the denominator of transfer function.
Yeah. Like at the end it'll look like something like this. It'll be like
So
two.
if you change H3, you change the denominator.
Yes.
So that's it. So you change the system response.
Yeah, okay, so it changes the system response, right?
Uh-huh.
So with that new denominator,
Oh.
to check if it's oscillatory, I just see if there's any complex roots. And if there are complex roots, then it's oscillatory, right? But then so when I changed like the different cases of H, then all the cases got complex roots, even though, so I did it both on mathematical thing. So some of the cases in MATLAB were real, were like just no oscillation, but then when I did it mathematically here,
So you have oscillation, and then you have to consider the damping factor. The damping factor will make the oscillation to disappear soon or disappear later. So the damping factor also depends on the denominator of transfer function.
how do you work out damping factor if it's a cube? 2 laws all at once. Like 3 laws all at once. Is this in your lecture notes?
That is from the fundamental mathematics. You try to define a fundamental. Something, for example, is key plus A is plus B is C, okay, and then S plus E. Okay, so you can always have something as squared there, so that's right. So the S squared is your second order term, so you can find out the second determinant factor.
So then what terms do I put here?
Huh? Depends on the numerical values and then you can
Wait, so if I have something like this was my new. So like, these are the 3 cases I took. I take like putting in a difference H3s. So
about the interpretation, what you discover by changing the H1, 2, 3?
H1, 2, 3, or just changing H3.
You also change H2 and you also change H1.
Yeah.
So what is the discover? What do you discover?
H2 was this one. Oh, H2 was moving the roots to the left hand side. So if H2 was bigger than this other number, it'd be exponential. So you had to make H2 smaller to bring all the roots to the left hand side. And then H1 was just like changing the game to something like just relative values up. But then yeah, H3 is the one I'm confused about because like when I do it on paper, it shows all of them should be oscillatory. But when I do it on MATLAB, some of them are like straight to the steady state, others it's like 0.1, S plus 0.1, S plus 1, I got it straight to a steady state, and then S plus 2 I got as it's a little bit oscillation. So I don't understand like how come when it's even though like here it says there's
No,
complex.
in the assignment, right? Initially, H1, 2, 3 all equals 1. And then you start changing H3.
Started with H2.
You start changing H2,
H2 is first.
first. So you start changing H2 first. And then your H1 is still 1. H3 is still 1. Then etc.
Yeah.
You change one by one.
Yeah. So I'm using the new H2 value here. But then, so could you explain this part again? Like, how do you find? Because you said damping factor also affects, like, whether or not it oscillates.
In example, it is S plus A, S plus B, S plus C.
Yeah.
So we have something, what is it?
That's two.
Okay, whatever. So if you change Ht equals S plus A, then Ht equals S plus B, S plus C. Okay, H2 S plus B. So it becomes K S plus B. So it is all second order system.
So you only consider the open loop.
So that what is the essence of the Boplan method?
So like see frequency, how frequency affects like phase.
The essence of the Boplan method is that we can examine the open loop response so that we can find out the closed loop response.
So then for this section, I shouldn't be using the big one. I should only use the G.
In your whole plot, we should use the open loop. And then the final response, we should consider the closed loop. Okay?
So this is wrong then, because I shouldn't be using. Okay, I'll think of it. Okay.
So we should draw this one.
记不清了。
log 有什么？因为那个是能看出来的。从理论上来说的话，去掉两个成本会导致系统更来这儿。它不是20 S 这个是那个距离。那现在其中一个对，把其中一个去掉，但是去掉 S plus 0 1呢，还是哪个？但是从图上来看，我看这个是。是去掉这个就
你可以对照这个小的法，它有3个，可以分开。
对。
三个都可以在这个什么上。
对，那肯定是越小就会单对。
你把它这个0.1很少的离网很大的这个题，才可以把它
就不是所以它会有 solution。
你看，去的其中一个，去的其中一个，去的第三次，后来就是2、3、4，这个变成一个
对，我刚才也是这样算的，但是
对这个的关系，
这个是 Excel 是 around 1，但是如果含有这个部分的话，它就大一点。
使用者跟着第二个系统，如果你天数有一个天数比 S， 然后这个它
会变，对。但是我刚才也是这样算，但是算出来跟我想的不太一样。如果去掉这个的话 ，Excel 是稍微大一点点，然后但是如果是去掉另外一个的话，含有这个0.1的话，它是远大于大概是2。我看到，这个怎么说的？就是我们对我们看的时候，从理论上分析也是分析 GH3，对不对？我们不会分析这个，虽然但是我们画图的时候应该是画这个，画图的时候是画这个，不是画这个啊，不是，就是他说那个里面有明确的说用 feedback 这个 command 那个。对 time response 肯定是 close response， 对。然后是通过调整这个 open loop 之后去看那个 close loop 里面的真正的时域的小数。那但是刚才这个 time 之后，它分别画了3条曲线，一个是这样的，这是那个去掉 x plus 0 1，一个是再稍微有一点是去掉 s plus 2，另外一个是有极限的，是去掉 s plus 2。所以，但是怎么从理论上？
把这个去掉，就
那为什么这个会大于去掉 S 3.1，这部分就是高是高，这都很大，对，是很大，这个大就不会有。可是求它是小的，因为你可以看一下 S plus 1 plus 2的话是 S square plus 3S plus 2，所以它应该是3除以2除以根2，对，所以它是1.5除以1.4，大概约等于1。是跟那个相反。但是如果是0 S plus 0.1 S plus 2的话，就是 S square plus 2.1 S plus 0.2，然后这个就是2.1除以2乘上根号0.2，这根号0.2大概是0.4几，这是2乘上0.45，好像是0.9，所以这个应该是大约是等于2，然后这个又是反过来，不太奇怪。对，
就是这两个乘起来刚刚好，乘起来刚刚好。哦，如果乘起来刚刚好的话就不一样了。哎，这个球来自对的，是哪个球？如果是根号，永远都是根号这个数，对吧？啊，不对不对，这是 b 加 c， 不是 b 加 c。应该是对，那就是 b 加 c 除上对。那是去哪个
没有记得清楚。
在10日里面。
老师刚好也就这个意思，就跟他那不同的日期，只要他们得到图分析一下就好了，是吧？没必要买新买手给的地方。
但你结果是对的。 画着画这个，
开始就错了。
我这是1号。